Today we're going to look at a few various topics surrounding functions, a few different ways that we can describe functions, and some different types of functions that we might run into that we haven't discussed before. Our first topic is even and odd functions. You'll remember from when we were talking about graphs of equations that we talked about various symmetries that the graphs of an equation can have. An equation can be symmetric about the y-axis, symmetric around the x-axis, or symmetric around the origin. And the same sorts of ideas are going to, of course, apply to the graphs of functions, because the graph of functions are just a form of graphs of equations. Now, because the graphs of functions have to pass the vertical line test, symmetry around the x-axis isn't something that we encounter in functions generally. And so we are only going to be interested in two kinds of symmetry with functions: symmetry around the y-axis and symmetry around the origin. And when the graph of a function has one of those two types of symmetries, we say that it is either an even function or an odd function. So let's describe what each of those mean. A function f of x is called even if its graph is symmetric about the y-axis, i.e., if a certain algebraic condition is here. Now let's think about what it means for a graph to be symmetric around the y-axis. We've seen a few graphs of this type so far. In particular, a lot of the parabolas that we've seen have this property. So let's suppose that we've got a function here, and it has a graph that's symmetric around the y-axis, meaning that if you were to put a mirror straight up on the y-axis and look at the reflection of the graph in the mirror, it would lie exactly on itself. Or if you were to spin it around the y-axis 180 degrees, then the graph would lie on itself again. And one of the ways that we can describe this is by looking at points that lie on the graph. If the point a comma b lies on the graph of a function, and the graph of that function is symmetric around the y-axis, then that means that the point negative a comma b has to be on the graph also. So that this means that f of a equals b, that's what it means for the point AB to be on the graph, but we also have that the point f of negative a equals b. So in other words, in this case, we get that f of a is equal to f of negative a. And this is an example of the equation that we use to detect whether a function is even, that is, symmetric about the y-axis. So it's going to be symmetric around the y-axis if and only if f of x equals f of negative x. Actually, I want to write that in the other direction because of what's going to come later. So if and only if f of negative x equals f of x for all x in the domain of f. So remember that when we looked at the transformations of functions, putting a -1 in front of the x, in front of the input to the function, reflected the graph across the y-axis. What an even function has going for it is that when you do that, when you reflect the graph across the y-axis, nothing changes. You get exactly the same thing back. And so that's what's being stated algebraically here, that's the algebraic version of the geometric picture over on the right. So that's what it means for a function to be an even function. Now, an odd function will be symmetric not around an axis, but around the origin. A function, f of x, is called odd if its graph is symmetric about the origin, i.e., if, and again, we want an algebraic description of what's going on here. So let's look at an example. Now, if a graph is symmetric around the origin, that means that it has some sort of shape, maybe like this. Where if you were to say put an axis, a needle right in the origin, and then spun the whole graph around on the plane 180 degrees, it would exactly lie on itself again. And the way that we can see that in terms of the points is the following way. If the point AB is on the graph, then the exact opposite point, the point exactly on the opposite side of that one from the origin, is the point negative A, comma, negative B. And when the graph is symmetric around the origin, then every point A, comma, B on the graph has to have its corresponding point, negative A, comma, negative B, also appearing on the graph. Now, if we express this in terms of what it says about the function values, this is saying that f of a equals b, and f of negative a equals negative b. And so we conclude from this, or another way of writing this down, is that f of negative a is equal to negative f of a. So in this case, f of negative a is negative b, and f of a is b, so f of negative a equals negative f of a. So this happens if and only if f of negative x equals negative f of x for all x in the domain of f. So when we have a function and we want to know whether it's even or odd, there are two ways that we can do it. We can either graph the function and just look at the function and say, is this function symmetric around the y-axis? If so, the function's called even. Is it symmetric around the origin? If so, then it's called an odd function. And if neither one of those is true, then the function is considered neither even nor odd. It's important to note that not every function satisfies one of these conditions. In fact, most functions we deal with are going to be neither even nor odd. However, the functions that do satisfy one of these conditions are helpful in a lot of things we want to do because they have a lot of symmetry that we can exploit. The exact way that we exploit that depends very much on the context. But one way that we can use it is in help with graphing. If we can use algebra to tell us that a particular function is either even or odd, then we can use that information to help graph the function, similarly to how we used symmetry to graph equations earlier. So the fact that we have a similar algebraic condition here for the two properties of even and odd suggests a strategy for detecting whether a function's even or odd that we can use pretty much all the time. So, to check if a function is even, odd, or neither, we do the following. Step 1, we evaluate f of negative x. And then, of course, we want to try to simplify. And then step 2, we check it against f of x and negative f of x. If f of negative x equals f of x, f is even. If f of negative x equals negative f of x, f is odd. And if neither holds, then f is neither even nor odd. So let's take a simple example. Let's ask, is the function f of x equals x to the fourth even, odd, or neither? Well, the way that we answer this is we say, what's f of negative x? We want to evaluate what f of negative x is, simplify it, and see what we get compared to the formula defining the original function. So f of negative x will be negative x to the fourth, because of course we replace the x in the original formula with negative x that we're plugging in. So negative x to the fourth we can rewrite as negative 1 to the fourth times x to the fourth, because negative x is negative 1 times x. Now negative 1 to the fourth is going to be 1. Negative 1 raised to any even number is just 1, so we get 1 times x to the fourth, which is x to the fourth. Now we have simplified that expression as far as possible, and so we say, does this function equal the original function? And in this case we see that it does. We get exactly the same formula out of it. If we plug negative x into the function, we get exactly the same expression out as if we plugged x in. That means that the points on the right side of the graph and the points on the left side of the graph are exact mirror images of each other. So since f of negative x equals f of x, f is even. Let's see some more. So let's ask, is f of x equals x to the fifth plus 3 even, odd, or neither? And let's see. We're going to take f of negative x and we're going to see what we get. So here we'll get negative x to the fifth plus 3. Now negative x to the fifth is the same as negative 1 to the fifth times x to the fifth plus 3. And negative 1 to the fifth is equal to negative 1. So we get negative x to the fifth plus 3. So now we look and see, does f of negative x, the thing we just evaluated, equal the original function? And we can see that it doesn't. It's got a negative where the original function didn't have one. So f of negative x does not equal f of x. So that means f is not even. So the next thing we ask is, does f of negative x equal negative f of x? Sometimes it's not super easy to tell whether this is true. So sometimes what you want to do is to just write out what negative f of x is. In this case, negative f of x is negative x to the fifth plus 3. And if we distribute that negative through, then we get negative x to the fifth minus 3. And so now we can compare the expression we got out of f of negative x with the expression negative f of x. And we ask, are they the same? Well, again, they're not, because now while the x to the fifth term, or the negative x to the fifth term, matches up, the constant term doesn't. We went from a plus 3 to a minus 3. So we have that f of negative x does not equal negative f of x, so f is not odd. So f is not even and f is not odd. So f is neither even nor odd. All right, so then let's look at one more. So let's look at, is f of x equals x cubed plus the cube root of x even, odd, or neither? Well, let's check it out. So f of negative x will be negative x cubed plus the cube root of negative x. Now, just like we did before, negative x cubed becomes negative 1 cubed times x cubed. And then the cube root of negative x, we can actually split that up also and write that as the cube root of negative 1 times the cube root of x. And that's typically what you want to do. You're trying to basically simplify this expression and algebraically manipulate it, massage it into a form that's as close to the original as you can get. You're trying to make this expression equal f of x if you can. So in this case, we get negative 1 cubed is negative 1, so we get negative x cubed. And then the cube root of negative 1 is also negative 1. So we get plus negative 1 times the cube root of x, so we get minus the cube root of x. And this is because the cube root of negative 1 is negative 1. So we see that f of negative x does not equal f of x. It's got the x cubed and the cube root of x terms, but they've got negatives in front of them rather than positives. But we have that f of negative x equals negative f of x. Notice that f of negative x is exactly the original function, but with everything multiplied by negative 1. So that tells us that f is an odd function, meaning that its graph is symmetric about the origin, and there are other kinds of symmetries that we can use there. All right, so this is basically the way that we check and see whether a function is even, odd, or neither. This is what it means for a function to be even or odd. The last thing that I want to mention is a shortcut that you can use to tell whether a function is even, odd, or neither, that also explains why we use these terms. So let's look at the following fact. If f of x equals, let's say, x to the, a1 x to the b1 plus a2 x to the b2, if the formula for f is a polynomial, something like this, a sum of a bunch of terms involving x's raised to powers, and all the bi's, all the powers on x's, are even, then f is an even function. And then if if all the BI's are odd, then f is an odd function. So, for example, if I look at the function f of x equals 17x to the 8th minus 3x to the 6th plus 7, this is even, is an even function. Because the powers on x's that are in this expression are 8, which is even, 6, which is even, and the constant terms are actually seen as being multiplied by an invisible x to the 0th, because x to the 0th is 1, which is even. So constant terms are also considered to have even degree. So that means that this function is an even function. And if I take g of x to be 20x to the 7th minus 3x cubed plus 12x, this is an odd function. Now, it's important to note these are not the only even and odd functions. For instance, we just saw an odd function in the last example that doesn't satisfy this pattern. However, if you happen to see a function that's defined by a polynomial where all of the terms have even degree, then that function is an even function. And if all of the terms have odd degrees, then that function is an odd function. And so that's sort of why we come up with these terms in the first place and use them to describe what's going on. All right. Next piece of terminology that we want to use to describe functions is we want to describe the intervals on which they are increasing and decreasing. So the technical definition for what it means to be increasing or decreasing makes it look a little bit more complicated than it actually is. I'm going to start with the technical definition, but then we'll see very quickly that it's that is more intuitive than the definition suggests. So a function is increasing on an interval on an open interval AB if whenever x1 and x2 are in the interval AB and x1 is less than x2, we have that f of x1 is less than f of x2. A function is decreasing on the interval AB if whenever x1 and x2 are in the interval AB and x1 is less than x2, we have f of x1 is greater than f of x2. And then finally, a function is constant on an interval AB if whenever x1 and x2 are in AB, we have that f of x1 equals f of x2. So this is the technical definition of what it means to be increasing and decreasing. Let's think about what this means for a second. If we look at the graph of f, which is what we're going to be using to really study this, what this first condition, the increasing condition, is telling us, is that if x1 is less than x2. That means that if we're looking at two x values on the graph, and x2 is bigger, so x2 is further to the right, then f of x1 is less than f of x2. That means that the y value on the graph corresponding to x1 is lower on the graph, is smaller than the y value corresponding to x2. What this means is that on this interval we have a graph that looks basically like this, that's sloping upwards when we read it from left to right. Similarly, a function is decreasing when the function is sloping downwards when we read from left to right. And a function is constant when it's flat when we read it from left to right. Another way of thinking about this is that a function is increasing if it sort of has positive slope. Now, only lines have slope, but this is the same sort of idea that we had when we talked about positive versus negative slope. Those same ideas apply to talking about increasing or decreasing functions. So let's make this, let's write down this intuition. So a function is increasing if its graph rises as we move from left to right. It's very important that we only read graphs from left to right when considering whether the function is increasing or decreasing. And we're decreasing if the graph falls as we move from left to right. So let's take the following example. On which intervals is the function f of x equals x squared increasing and decreasing? So to answer this question, we are going to be looking at the graph. The graph is pretty much going to be the only tool we have to work with this. It turns out that there are other methods that can be applied here, but they're fairly advanced, and in fact, the best ways of doing it use calculus. So we are familiar with the graph of f of x equals x squared. We know that it hits the origin 1, 1, it goes 0, 0 rather, it goes to the point 1, 1 and the point negative 1, 1 like this. And so if we want to see where the function is increasing and decreasing, what we want to do is look at the function and say, or look at the graph rather and say, where is this graph rising and where is it falling when we read from left to right? So let's start over on the leftmost part of the graph. If we follow, let me take something that shows up against the blue a little better. If we look at what's happening over here on the leftmost part of the graph, we can see that as we move from left to right, the values of the function are falling, that we are getting lower and lower as we move from left to right along the graph until we finally get down to the origin here. So let's stop there and see what we can say about this. On the part of the graph that I've highlighted in yellow, we say that the function is decreasing because the function is falling as we move from left to right. If I look at a point with a higher x value, it will have a lower y value. So we say that the function f is decreasing on the interval. And now when we describe the intervals where a function is increasing or decreasing, we are describing the x values that correspond to those places where the function is increasing or decreasing. When we talk about the intervals where a function is doing something, we're only ever talking about the x values, not the y values. So when we go to this problem and we say, where is this function decreasing, we're only going to be considering the x values here. So we're going to be taking this yellow region and basically dropping it down onto the x-axis, or looking at its shadow, sort of like how we did when we were finding the domains of functions. And so here we can see that this yellow interval contains everything on the graph up to the point 0, 0, and we're interested in the x value of that point. Furthermore, at least here, we are only going to ever be considering open intervals for a function being increasing or decreasing, meaning that we're never including the endpoints. All of our intervals will just have parentheses on the outsides. So this function f is decreasing on this yellow interval on the x-axis, which is the interval from -infinity to 0. So this means that if I take two numbers in the interval from -infinity to 0, two x values, whichever one is the bigger x value will correspond to the smaller y value. That's what it means for the function to be decreasing on this interval. Okay, so now we were decreasing for a while, we got to 0, 0, and now we can see that afterwards we start increasing, we start moving upwards. And now if I take two x values on the right side of the graph, then the larger x value corresponds to the larger y value. And so we say that the function f is increasing on the interval from 0 to infinity, because it's increasing everywhere to the right of 0 on the x-axis. So a couple things to always keep in mind when we're doing this. We're only ever talking about the x values when we give our intervals where the function is increasing or decreasing, and we always read from left to right. Let's see another example. Let's find the intervals where the function f is increasing and decreasing. Or let me say increasing, decreasing, and constant. Its graph is below. Let me go ahead and give myself a grid to work with. All right, so let's take our function and we want to get a few points here. And we'll do this. And up like that. And I want to note a few points that are going to be relevant to us. All right, so we've got the point -9, 2, -4, comma 6. We have the point 4, comma 6 here. The point 11, comma 2. The point 14, comma 1. And the point 17, comma 4. So let's try and identify the intervals where this function is increasing, decreasing, and constant. So increasing, decreasing, and constant. And actually, let me move these down here. We might need a little more room. All right, so one thing we can do is just start moving left to right rather than trying to look for all the intervals where the function's increasing or where it's decreasing or where it's constant, anything like this. I find it's usually more helpful to just start reading at the left end of the graph and move to the right. And that way you cover everything, and for each interval you get, you just record it down below. So for instance, this first part of the graph, from the point negative 9, 2 to the point negative 4, 6, we see is increasing. It actually looks like it's a line segment, so it has a slope, and it's got a positive slope. It's moving up when we move from left to right. And so the x values associated with those points are what we use to describe the interval where the function is increasing. So here we see that the function is going to be increasing on the interval from negative 9 to negative 4. Now there might be more later. We're just recording that for now. All right, and let's see what comes next. Next, we've got a section of the graph which isn't changing. It's not going up and it's not going down. This is an example of an interval on which the function is constant. The function's not increasing, the function's not decreasing, it's just staying at the same level. No matter what value of x you pick from the red interval, the output of that function, the y value associated to it, will always be 6. And so this is a section of the graph where the function is constant. So the function is constant on the interval from negative 4 to 4. All right, next we get a part where the function starts decreasing. It starts sloping downwards, and then it starts to shallow out, get shallower, but then goes back down. So in this case, even though the graph flattens out sort of instantaneously there when x equals 11, it's still continuing to decrease because we never get like a solid segment of horizontal graph like we did on the previous interval. We don't actually say that the function is constant on any interval here. We actually do say that it's decreasing the whole way down, because if I choose any two x values on this graph, the x value further to the right, or on the green interval, the x value further to the right will correspond to a y value that's lower. So this function really is decreasing on the whole interval from 4 to 11. And then finally, we've got a last bit where the function's increasing again. So we get the interval from 14 to 17. So we say that the function is increasing on the interval from 14 to 17, and whenever we have multiple intervals where the function is increasing, we can express it several ways. Pay attention to how the homework asks for it. It might ask for a comma-separated list of intervals, or you might need to give it as a union of intervals the way that we have here. From a purely mathematical point of view, expressing things using the union is somewhat nicer. But even that depends on the context. So just pay attention to how the problem is asking for the answer to be given. And this is pretty much all that there is for the question of when a function is increasing, decreasing, or constant. We can pretty much read it off directly from the graph, and as long as we are able to graph the function, we're able to answer these questions. Now, a topic that's related to this question of where a function is increasing, decreasing, or constant is the question of local maxima and local minima. That is the places where the function reaches a peak or a trough or valley. So let's talk about that. That's our third topic. So let's talk about local maxima and minima. So for this, let's start with the graph. Let's start with a graph of a function. And let's say that it looks something like this. When we look at the graph, you can see that there are various places where it sort of turns, where it changes from increasing to decreasing, or vice versa. You'll notice that these are also places that sort of either sit at the top of their neighborhood or at the bottom. So this point over here, this red dot is lower on the graph. It has a smaller y value than any of the other points on the graph that are close to it. There are other lower points over here, but if we restrict our attention to just what's happening near this red point is the lowest. So this is the lowest red point in its immediate neighborhood. And so we call it, or rather we call its y value a local minimum. Local means that we're only looking at the immediate neighborhood of this point. We're not looking at any other points around it, such as the tail off on the right side of the graph. And so this is it's local. And then it's a minimum because this point is the smallest, has the smallest y value of all the points around it. Exactly similarly, this point is called a local maximum since it's the highest, or its y value is the local maximum since it's the highest point in the immediate vicinity. So let me give these points coordinates here. Let's say that this is the point 7, 8, and this is the point -3, 1. And we'll say that this blue line is the graph of f of x, of some function f of x. So in this case, we would say that f has a local maximum of 8. And that's because this point here, that's at the peak of one of the hills in the shape of the graph, has a y value of 8. And we also say that it has a local minimum of 1, because if we look at the red point that's at the base of the valley over on the left side of the graph, it has a y value of 1. Now, again, the term local here means that we're only looking in the immediate vicinity of this point. The fact that there are points over here on the left that have higher y values than 8, or points over on the right with lower y values than 1, don't matter to this question. These are still local, well, we have one local maximum and one local minimum. The term maxima and minima, by the way, are the plurals. Maxima is more than one maximum. Minima is more than one minimum. Finding local maxima and minima are, again, something that we are only going to be doing by using the graph. It's something that, again, calculus gives us tools to handle more algebraically, more symbolically, but we are going to use the graph to do it. So let's look at one example. Let's find the local maxima and minima of the function with the graph below. So let's take a graph. Oops. And we want the following graph. All right, and we have these points at -2, -2, 3, 1, and 7, -1. What we want to do to find the local maxima and minima is we just want to find all the points that lie either at the bottom of a valley in the graph or at the top of a hill. Places where the function switches from either decreasing to increasing or increasing to decreasing. So, for each of these, we can identify whether that point corresponds to a local maximum or minimum. The point 3, 1 is going to correspond to a maximum because it's at the highest point of its immediate vicinity. The point -2, 2 is going to be a minimum because it's the minimum, it's the smallest point, the lowest point in its immediate vicinity. And the point 7, -1 is also the lowest point in its immediate vicinity. And again, here we're looking at the y values. We're looking for points that have the smallest y value among all points in its vicinity. And so we would say that this function has a single local maximum of 1, because that's the y value corresponding to our point that sits at the top of a hill in the graph. And this function has 2 local minima. It has a local minimum of -2 coming from the first point on our graph, and a local minimum of -1 coming from the other point. So in particular, notice you can have more than one minimum, and you can have more than one maximum even. They don't have to be the same number. And in fact, for particularly complicated graphs, you can even have local minima that are greater than some of your local maxima. It is also quite possible for a graph to have no maxima or minima at all. So, for instance, if we take a typical linear function, this function has no local maxima or minima because it has no hills and no valleys to work on. However, this isn't even restricted to linear functions. If we look at this green function here, which is some variation on the x-cubed function perhaps, it also has no maxima or minima because even though it has some curves to it, it's not just a straight line, there's still no valleys and still no still no peaks. There's no place where this function changes from increasing to decreasing or vice versa. Find the minima and maxima of a function are important points in the function that are related to where it changes from increasing to decreasing and vice versa, and our best way of finding them is using the graph.